Hello, everybody, and welcome to the digital materials session on creating a digital twin of a nonwoven. My name is Andreas Grieser. I will be presenting this topic, but the slides I will be presenting was a lot of work for a lot of people, especially Nelly, who is also here. It's new with us, but already created a few nice slides in here. A few are from Eric and a lot of different people. I didn't want to write them all down here. It's more like a cooperative work. So first of all, if you have any questions, just ask away. It's better than me talking for like 2 hours here. So just interrupt me. Also, the people that are online, just ask questions in the chat, and then Christian will interrupt me and we'll try to answer your questions. We'll start with a short introduction on the topic, what is a digital twin? Because when I created that slides, I thought, yeah, maybe we should talk about that first, and especially how it's done in Geodict. Afterwards, we will get to the workflow part where we present a few of the tools we need to create digital twins in Geodict, and then the actual digital twin Geo app, which will be a bit of a technical part. And afterwards, we will show some results where we see results of flow simulations and stuff like this to compare the digital twin to the actual structure. So let's get started. Well, first of all, what's a digital twin? Classically in the industry, it is normally something like a CAD, a model of a real part. So it could be a model of an engine, for example, that accompanies a product through its life cycle. From production, maybe during production, track which parts have been installed, what tolerances were realized during production, and so on, even maybe through the lifetime. So that's usually a very concrete model of one part where you have defined geometries and stuff like this. When we talk about material science, the things are a bit different because we don't really care about the fibers in one sample. So if we have a nonwoven, like in this example here, you don't really have a benefit of tracking if the fiber is moved like 1 micron to the left or to the right. But what we instead want to know is what are the statistical properties of this material that describe the geometry. And for us, that means we call it a statistical digital twin. And it is not an exact representation of a real material, but you can think of it more like a set of parameters that you can use with FiberGeo or whatever Geodict modules to create something that has a similar geometry to the original material, and also ideally physically the same properties if you, for example, simulate flow through it. So why do we want to create a digital twin in Geodict? Well, I think it has been talked about a bit already this morning. First of all, creating such a digital twin gives us a lot of insights into the material. So we really understand it. For example, have we a material with multiple layers? Are there multiple fiber types in there? Is the orientation maybe changing throughout our material? Stuff like this. And then once we have created such a material, we can actually start to play with the parameters. So we can optimize the material for certain properties, filtration applications, for example, to optimize dust holding capacity or pressure drop. Nonwovens in many applications, for example, also optimize mechanical properties if you're interested in this. So it gives us a lot of options to play with the material and see how it would behave if we change any geometrical property. So how do we create a digital twin? Well, first of all, we start with our real material over here. And then we have to take some kind of image, because if we just have the real material, it's a bit hard to estimate the geometrical properties. I mean, some we may know, maybe from the production process, but definitely not everything. So ideally, we take a CT scan. And we get something like this here, where we have our volume, and then we start with the image processing inside of Geodict. We import it, we maybe align it with the XY axis. We create a segmentation. That part is really important, and we'll talk about a bit more about that later. And then we can actually start to analyze the material and obtain our geometrical properties that we want to maybe modify later on. So for that, we have a few modules that we can combine, and then we put that all inside of, for example, FiberGeo to create actual realizations of our digital twin. How was that done in the past? It was quite a bit of work. I guess some of you know this. You spend a lot of time with trial and error. Even if you're an experienced user, usually it's not done with just doing a few realizations. You have to do a real loop of, okay, I realize something, I measure on it, does it match, is it okay? No, maybe yes, okay, then and on we go. And usually also you need a lot of Python programming skills to create complex models. Ideally, that should be more easy now. Short overview about the tools we need in Geodig to create a digital twin. We have, first of all, as I already mentioned, import geo to import our scan, do all the image processing, and finally do the segmentation. Then we have FiberFind to analyze fiber geometry. For example, so basically everything, we get the orientation, the diameters, the trajectories, curvature, whatever you can think of, we basically can compute it. And then we also, for this case, need MATDICT. Usually MATDICT is always very useful to get, for example, porosities, and or for these sheet-like non-woven materials, estimate the density distribution through the Z direction and estimate the thickness of the material. Yeah, all these modules, they give us the properties of our material. And then, of course, we finally also need FiberGeo to create our model, because, well, without that, it wouldn't be so fun. So I have that now visualized in this nice slide that I probably will forget half the things I wanted to say about it. But basically, you can see here the whole loop of creating a digital twin. We start from the CT, we do all the analysis stuff with FiberFind, MATDICT, whatsoever. We get a range of results, and these are then again inputs for our non-wovens digital twin app. So diameter distributions, lengths, orientation, curliness, curvature, they all can be used as inputs in the digital twin app. And the digital twin app will, on one side, use some parameters directly, and others, why did it do this? Will have to be optimized. And then we get to our FiberGeo result. Here's a first screenshot of what the UI of the statistical digital twin app looks. So you have as input parameter, of course, the result file name like everywhere else in Geodig. Then you have the identify fibers result that is used. You have a downsampling factor that's just for speed up. The option to optimize the thickness and density distribution, and some parameters for the global optimization I will talk about later. And what internally then is happening is that some parameters are directly written, read from the inputted FiberFind result, for example, the domain size and the diameters. But some other parameters like the curvature, they have always be kind of a problem, because they the way FiberFind computes them cannot be entered into FiberGeo directly, because it's a bit more difficult to describe them. So for these parameters, an optimization will be done in the app, and the parameters will be fitted to generate a geometry that has similar properties if you run FiberFind on them again. So then have a first test. We have here one real scan and one FiberGeo generated non-woven from the app. Maybe we will make a everybody raises his hand who thinks that the left one is the digital twin, and who thinks that the right one is the digital twin. Okay, you were right. Yeah, so basically you can these fibers that are bundled up give away that is the digital twin, and basically all the people right, this is the digital twin. Okay, yeah, and here we have the result. So it's the same pictures as before, and we have a fiber curvature distribution for in red, the original material, and in blue, our digital twin, and also a permeability calculation we did here, which is well within 10%. So that's a very nice result. So much for the introduction and a bit of a teaser for the app. And now we will get into more detail. How do we do all this in Geodict? Which modules are required? And then a bit in the technical part. So short overview, the import and image processing tools in Geodict, because we don't have an image processing session this year. So it's part of this session. We have basically everything you need for image processing in the software. We have the import tools to import many formats that exist. And if you have one that doesn't exist, we can probably just add it in. Just ask us. Cropping and alignment tools and scaling of gray values and the whole resolutions all in there. Then we have the image processing tools to do filtering, remove gradients or flickering in your gray values, filter noise out, sharpen the image, remove streaking and ring artifacts. And also what we have since last year, I think, is the AI-based image enhancement. It's not so interesting for fiber media because usually the image quality is quite good. But you can, with this tool, enhance an image using a neural network that you have trained on some pairs of data sets before, where you maybe have some scans of high quality that were scanned with a long scanning time, and you have some scans of low quality that were scanned really fast. You can use them to train a neural network to basically always use the fast scanning method and still get the high quality image results. So then the next part is the segmentation. That part is really, really important because if you do the segmentation wrong, you will end up with results that just don't match reality. So especially for fiber materials, it can be a huge difference if there's like 1 voxel more part of the fibers or not. Your permeability, for example, will be way off. So getting a good segmentation is kind of important. We have a lot of segmentation tools in Geodict. We have the usual thresholding methods. We have watershed-based methods, and we have also what is shown here, the trainable AI segmentation. I think it was shown off earlier today already. Yeah, so a lot of tools to segment and really take care of your segmentation. And finally, we have the analysis tools like FiberFind to get the geometrical properties we need for our digital twin. This now leads us into the workflow. Step 1, importing and doing the image processing. Well, as I mentioned, you can basically load all the formats. You will import your CT data. You get the image processing UI in Geodict, where I have just a global thresholding open here and some 3D volume in memory, of course. You can visualize, have a look at it. There's, for these nonwovens, usually not a lot of work to do. The scans usually have high quality, but a few things, maybe there's noise in the pore space that happens sometimes. So maybe take care of this. And what also is important, especially for the digital twin, is making sure your medium is straight and aligned with the XY axis. If you want to do, for example, analyze the thickness and your material is not straight in there, then the thickness estimation will be way off. So there's tools in ImportGeo to take care of this. And then we get to the segmentation. So I have now here a nice slide on the AI segmentation. That is a 3-phase segmentation you're seeing here. If you have simple 2-phase segmentations, often Otsu method can be enough. But if for cases like this, where you have a lot of these pores that have basically the same gray value, maybe I use that pointer so the online people can see it too. where you have pores like this, where basically the center area has the same gray value as the matrix material in this case around here, and only the edges give a real contrast, then simple thresholding won't do it. And this is where the AI segmentation in this example shines, and you get a nice segmentation where the pores are segmented from the matrix and the fibers. One enhancement we have done to this this year is that we can now do multi-channel segmentations with the AI. So if you have a FibSEM scan, you can load up normally you have like 2 or 3 detectors that give you some different images. You can see them here on the left. So in the top one, there's more contrast between the background material because we are seeing into the pore space here because it hasn't been infiltrated. And you have more contrast between that and the slice that is actually the front than in the lower image. So if you look here, that is basically the same gray value. But in this image, you have more contrast between the materials. So the binder here and carbon black domain has more contrast to the active material. So it's useful to feed both images in. And we have here an example that my colleague Janine did, where she won in the upper segmentation. We see here only trained on one image, and in the lower ones she trained on both images, in both cases using the same training data. And as you can see, there is way less errors here in this area of binder. I think she actually used a bit too much labeling because also that result is already pretty good. Another thing we have improved in this year's release regarding segmentation is the AI Magic Brush, where you get as a segmentation, like a separation of your scans into these little cells here, and you can control the size of the cells, adjust it to the feature size of your scan, and then you can easily create label data, and it's just way faster. So doing something like this before may have taken like a few minutes, and that's like 30 seconds now. So it's a lot faster and easier if you have nice edges in your material, get to a segmentation way to your training data for the AI way faster. Yeah, so to get back to our sample, well, in this case, I use just Otto segmentation, just calculate the threshold automatically and get your segmentation. It has its advantages. It is easily reproducible, and it's also a lot faster and less manual work. Oh, now that we have our segmentation, we can start analyzing the materials. So in our case, we run FiberFind AI to get an idea of what is happening in this material. And we also look at the density distribution in through direction. So if you have a medium with a gradient, we can reproduce this. So it's quite important. And I will talk a bit more about FiberFind now. FiberFind is not only FiberFind AI, but we also have the classical FiberFind, where we, for example, in this case here, can estimate the orientation without identifying the individual fibers. It is very robust. It also works if your resolution is too bad to identify individual fibers. Get something like this is a composite material. You can see here the change in orientation that is happening in the middle. You can get that with the FiberFind AI too, but in that case you need a high enough resolution to identify the individual fibers. And it also maybe depends. Sometimes it's faster, sometimes it's not. Yeah, the next thing we have in FiberFind is the diameter estimation. Again, we have the classical method that is working based on watershed and distance maps and some clever seeding algorithms. You don't need fiber identification for that either, but with FiberFind you get it too in one result without doing it individually. This one is, again, it's very robust as long as your fibers are roughly round and somehow resolved. So you don't need an image as well resolved as you need it in FiberFind AI. Yeah, so if you only need fiber diameters, that is also a way to go. Well, for our nonwovens, we also want the fiber length distribution. And that's then the point where we actually need FiberFind AI, and we also want the curvature, of course. So we, for the digital twin nonwoven app, we cannot, we need the AI part that does the individual fiber labeling, and we have a nice example here from the Digilog B project where such a composite material here was scanned and analyzed with FiberFind, and also experimentally the fiber length distribution was measured. And we have some nice agreement here in brown. We have the FiberFind result, the experimental result, and in blue we have the FiberFind result. So nice agreement for the fiber length distribution here, and yeah, that is also part of the digital twin nonwoven app that we need. Last slide about FiberFind is we have done quite a bit of improvement to that in Geodic 2024. We have trained a new neural network for randomly curved fibers like in nonwoven. It's now finally robust against the orientation of your scan, so you don't have to make sure that your fibers are oriented in the XY plane anymore. You can just use them however they were. It can now also work on elliptical fibers. Aspect ratio should be ideally somewhere above 0.6. And also the fibers that are fitted will still be circular. We don't have added support yet to create a model of elliptical fibers, but that is something we could do if someone is interested in this. We also increased the range of voxel diameters that is supported from back then 4 to 10, of 6 to 14 to 4 to 26. This is nice if you have a scan with really thin and really thick fibers mixed, so you don't get the artifacts in the thick fibers we've seen before, and still can work with the thin fibers. Or you would have to somehow split up the thick and the thin fibers and then do the analysis separated. Now you can just do it in one go and separate them afterwards if you want to. And we can now also work with fibers that have a varying diameter throughout its length. So if you have fibers that are thin and thick along its trajectory, that isn't a problem anymore now. But again, the fibers that are created for the analytical representation still will have the medium diameter of the fiber. But that's something we can also change if you're interested in that. Next slide is then about MATIC and the thickness estimation that was previously known as the 1D statistics. It now has a bit nicer name that is, I think, a bit more descriptive. We did a major rework on that. So the fitting models are more flexible now. You can also just say, compute me everything in here. So everything is a bit better in here. We have here gas diffusion layer, a woven gas diffusion layer actually, that I'm using as an example. Yeah, so that is just your tool to estimate the thickness of a material. As I mentioned, it assumes your material is aligned with the XY plane or one of the other major planes here, depending on what you select up here. And yeah, you can also just decide here, do I have inlets in the material? Do I have outlets in the material? Is it a gradient material? And so on. It's a bit easier to use. And you get a nicer report in the end, where you get, for example, the different estimations depending on the method you have chosen. Yeah, and before I think there was a complicated formula in here that then told you from this slice to this slice it is this, and then on the next slice is that. So it's overall a bit more user-friendly and powerful. Get also the plot is very similar to how it looked before, but the fit is usually a lot better now. We have another example here. It's now not a fiber material, but something different, just showing off how that could look in your case. And now that is actually the analysis for the nonwoven we have been talking about before. As you can see, there is a bit of a steep gradient here in the beginning and a more not so steep gradient in the end. That's probably to either how the manufacturing was. It's probably laid down on some kind of Förderband, conveyor belt, exactly. And then the fibers piled on it, or also during scanning, it was probably fixated to some kind of plate. That's why maybe on one side it is a bit more flat, and on the other side we have like a gradient running out. And yeah, there we have our thickness estimation down here, and that is just put into the nonwoven app to then optimize the thickness. Let's go on with the second part, where we actually get into more of the modeling part and how the app works in detail. To start with that, I will do a bit of an excursion on how fiber modeling is done in FiberGeo. So how do we create curved fibers as an algorithm from a amount of parameters that one can maybe understand? Well, in principle, we start with two segments of fibers that are randomly oriented to each other. And then we have to we add segments of a predetermined length step by step. And well, we somehow have to decide in which direction, starting from a point, should the fiber go on. So for example, we can go with maintain the previous direction. We can be pulled towards a global orientation. We can say, okay, we want to maintain the curvature, stuff like this. And all of this, of course, also depending on the direction, so anisotropic properties. I have a bit of a visualization here. So down here we see the FiberGeo UI to generate curved fibers. First parameter is the segment length. It's a bit not so nice that that parameter exists, but we are working on getting rid of it. And that is also a very important parameter already to determine how the fiber is curving. Then we have the local straightness. That is the parameter that basically decides, will my fiber keep its current direction or will it keep its current curvature? So if it is 1, it will keep the curvature. If it is 0, it will keep the direction. Then we have the global straightness. That is basically, does the fiber curvature care for some global orientation or does it not? So if that is 1, it will always be pulled back towards the global orientation, which basically means if you have like 0 up here and 1 down here, then you will end up with something like a sine curve. And then we have the randomness that is necessary to get some kind of deviation from a straight path at all. So, and get some random behavior in there. But as you already can see, it's not so nice that these parameters don't come out of FiberFind. Here's another visualization of how that works. Basically, we start from these two segments here. They are oriented, pulled from the global orientation tensor and have an angle towards each other depending on the randomness. And then the segments are added piece by piece until we reach the length we want to reach in the end. For the local straightness, that can look like this, where we have these two parts here. And now in the first case, we have a local straightness of 1. It means we want to keep the direction and the fiber will just move like this. And we have a bit of deviation depending on the randomness. If we keep the local straightness at 0, it will look like this. So the curvature will stay the same. And we have, again, a bit of deviation for the randomness. We have some nice visualizations, what that looks like if you keep the global straightness and local straightness both at 0 and just vary the fiber segment length. And you will end up with something that really doesn't look like fibers, but more like clumps of whatever, to something that slowly looks like more like fibers, spaghettis, and then something that could be a non-woven. So you see already the segment length parameter has a big influence. Of course, you cannot, the higher you turn it, at some point you just end up with basically straight fibers that sometimes have a kink. So going too high here isn't nice either. Yeah, so we have here animated how the fibers change if we change the global straightness parameter and keep local straightness and segment length constant. You can see how the fibers get more and more stretched, but they will still keep a bit of this what a sine-like shape in the end, because we have the randomness that is always going a bit away from the global orientation, and in the next step, it wants to be pulled back towards the global orientation. So that's why you not end up with perfectly straight fibers here. Also, you can see there isn't a lot happening in the higher parameters. Yeah, so that video is basically the same as before, but this time we change the local straightness from 0 to 1 and keep the global straightness, segment length, and randomness the same. See, the fibers get more straight and straight. It's a bit nicer because you don't get this sine-like shape effects in here. So if you want straight fibers, that is a good way to get straight fibers. But then you can also just use straight fibers and not not curved fibers. And then we have changing the randomness. And as you can see, that escalates really fast. So in the beginning, that was probably a valid range of parameters until we reached like something around 0.5. And I think then we had just a lot of kinks. Like for some, I have to switch to not having the laser pointer so I can control the video. You can see 0.05 still looks nice. 0.1, okay, for these set of segment lengths. And yeah, around 0.3, things start to look a bit. Oh, you cannot see that pointer here. Yeah, we get some kind of kinks in here, and just gets worse from here. So yeah, with that parameter, usually keep it low, or you have to also adapt the segment lengths and stuff like this. Basically, shorter segments, higher randomness again is kind of okay, but yeah, don't put that parameter too high. So that's it on the fiber curvature modeling. If you have more questions to that, just ask me later on and talk a bit about it. And now we get into the actual app. I already talked about that user interface a bit. And yeah, here, refresher. Well, what do we want to do in this app? We run fiber find. We read from the fiber find result domain sizes, fiber diameters, fiber volume fractions, the fiber orientation. And then we set up an optimization to find the curvature parameters based on curvature and curliness and the standard deviation of curvature and curliness. Yeah, we set up that optimization, we run it. That means we really realize a lot of fiber geostructures. And in the fiber geo result, we get, again, a curvature distribution, and we can compare that to our fiber find result and hope they match. And we can do that for a bit of, well, usually it takes a few hours. So one thing about the app is that it is not really intended to be used the way it is. I mean, you can use it the way it is if you have a nonwoven with only one type of fibers and one layer. That just works as long as the fibers are kind of round. But it is also more like a cookie cutter, because the app is set up in a way that you can easily change the parameters you want to optimize. You can change what targets you want to optimize. Basically, for example, at the moment, it's only optimizing for some geometrical parameters, but you can also put a Floadict run in there and then optimize for a certain permeability. And you can also optimize, change which parameters should be varied. You can, for example, introduce a second type of fibers with different diameter constraints and stuff like this. Unfortunately, and that's why we will go a bit into Python code now, you cannot do this through the user interface, but you have to go into the app and change the code. That's why I will be explaining a bit now how the structure of all this is and how you can easily change it to adapt it to your needs. Well, the first step in the app that is kind of most important is to set up our generators. That means all the functions we need to evaluate in each iteration of the optimization loop to create our structure and measure whatever targets we want to optimize. So in this case, I will go through a bit of a simplified version where we only have one step to generate, and that's a FiberGeo run to create fibers in here. We need to define this generator dicts list of commands. So in this case, just the command and the arguments. That means also somewhere before in your command, you have to basically have the default FiberGeo command in there and put in the fixed parameters, or you can just use the one that is in there. You can change it, or you can add even more commands. In this case, only FiberGeo, and yeah. Then we need to set up what parameters we want to change in our optimization. So we want to optimize to match the curvature of our curved fibers. So we, of course, we change a curvature-related parameter. In the real app, we have 4 parameters. Here we only have the local straightness parameter. Yeah, and it's set up this way. You have this this class is available in Geodict. If you have a Python macro and I import the opti-util class, you can then use this opti-parameter class. And it has a few parameters that I will be explaining now. Well, the first one is just the name that is used in logging and so on. The second one is the limits for the optimization. These are used in both cases, actually. It's especially important for the global. If you are using a global optimization loop to avoid running into local minima, we are using a global optimization loop and you just define the bounds. So actually they are chosen pretty wide here. You can make them smaller too. Yeah, and they need, of course, to be valid. So having a negative value in here will give you an error in FiberGeo, and that's not so nice. Then we need to set up the initial value. That one is not so important because it is only used for local optimization. And the app at the moment works that you first do a global optimization and then use the results from there to then do a local optimization to basically polish the result. So it does the initial guess basically for you. And the last one is actually the most important parameter. This one defines where it has to put the parameter in your generator list. So before we set up this generator dicts list, and with this parameter, we tell it, okay, in the first entry of this list, use this variable under the key generator1 curl local straightness. So in your FiberGeo result, in your FiberGeo parameters dictionary, you usually have something that is called generator1, and curl is the parameter of the curved fiber model, and in there is the local straightness variable. So this way, the class now knows where does this value have to go in the generation step. Next thing we need to set up is, of course, the values we want to optimize for. So how do we calculate an error? Again, we have the target value class for that. It's again set up with a few parameters. In the real app, we have 4 of them. Simplified example here, only one, only looking for the curl index. mean. Reality, I think it's curl index mean, curl standard deviation, curvature mean, and curvature standard deviation. First parameter is again just a name for logging. The second parameter is the reference value. So in this case here, it's just fixed 1.4. That could also be coming from your initial fiber find result. For simplification, I just put 1.4 in here. And then similar to the optimization variable class before, we have in the end we tell that class how to find this in your result, so in your generation result. And of course, now we have parameters set up and we have optimization targets set up. Now we want to use them. And for that, we have the OptiLoop class. There's OptiLoop global and OptiLoop local. One is for global optimization, where a whole parameter space is sampled to make sure you have not running into a local minimum. And the other one is then for local optimization. So if you have a good initial guess already, you can just use the local optimization. It's a lot faster. But what we do is first do global, use that as an initial guess for the local optimization. So this has a few more parameters, but the first one is again just a name. That's just because if you have multiple of these loops, the result file will show convergence plots for each of them, and you want a name to differentiate them. Okay, easy. The second one is our parameters. So like 5 slides before, we defined our optimization parameter P1, and we just put that in here. So here it's a list of with one entry. In reality, that will be a list of maybe 4 to 5 entries. Second parameter, the same for the optimization target. Again, here just one, could also be a list of any amount of parameters you want to optimize for. Then that is again important. That's our generator dictionaries that we defined in the first step, and where we have all the generation steps in there. And finally, we have these 2 parameters that control the number of iterations in your optimization that come just from the UI. And we'll talk about them a bit later. So now that we have everything set up, we of course need to run it, where we just call on our optimization loop variable the doOpti function and pass in the result file where it should write its intermediate results. And the output will be the optimal parameters it found. There's again a list of parameters, and we can just apply them to our generator dicts to have the current values written into the generator dictionary and use it maybe later on for a second optimization loop. So these were also the rough steps that are done in the code. Of course, there are some more details to it. It was a very simplified overview to give you the idea that you can easily exchange what parameters you want to optimize for. From the UI, it's a bit easier if you just want to use the default version that we have. You go into the generate nonwoven statistical twin app in the structure generation geo app menu. So basically you select in the geo app menu structure generation, and then on the left side you have our usual module GUI, and there is a combo box with I think 3 entries, and one of them is the nonwoven statistical digital twin app. And you end up with that user interface where you input the output result file name, the identify fibers GDR you want to use as a basis, downsampling factor. That is actually pretty useful because if you run it at full resolution, it takes way longer than if you just put like a downsampling factor of 4 or 8. You just have to make sure that your set height is divisible by the downsampling factor and your fibers are still resolved with at least 1 voxel. going on. Last few parameters in here are the iteration parameters for the first two, the population size and global iterations, are parameter of the global optimization loop. It's a bit unfortunate. The global iterations number 15 here is not really the number of iterations it does. The real number is something like the global iteration times population size times number of parameters, and I think there's a +1 in there too. So you end up easily with a lot of CyberGeo structures that are for the trash bin. And then you have the local iteration parameter, that is just how many local iterations are done. And because we now have seen a lot of code, I have here a little animation where we see how the FiberGeo structure changes during the optimization. So on the right side is where we want to go, and on the left side is just replay it, how the structure is changing. I've thrown out a lot of here and only took the structures where a new minimum was hit, because else it doesn't make any sense looking at it. But you can see how the fiber slowly, the curvature behavior is getting closer to what we have as a target over here. Okay. Then let's have a look at what the results look like if we compare them quantitatively. First of all, the app, as I already mentioned, produces a result file. And for every optimization loop you put in there, you get in the report something like this, where for the parameters you have used, you get the value that was found in here. That's of course also in the map file if you want to read that mechanically. And you also get a convergence curve. This one is a nice one because it's one of a local optimization that really looks like a convergence curve. For the global optimization, it usually jumps all over the place. But if you look at it very closely, you can see that there sometimes a new minimum is hit. Then we have, again, the visual comparison. So again, here on the left, what was generated. I think it's a different image from before because that was with the latest version, where some of the other images were with older versions. And on the right, the target we wanted to go to. So first step is always having a look at it. Does it look similar? Yeah, I think that looks already pretty good, but of course that doesn't really tell us a lot. We have another visual comparison looking at it from straight above. One thing one maybe can already tell is the usual issue you have with FiberGeo, that the real thing, of course, has a bit more inhomogeneity than the FiberGeo generated structure, but that comes down to having a large enough sample for your representative volume element. And then we also take a look to the geometric properties. So we have here the curvature distribution from our two samples. I think we had that before in the first chapter. And as you can see, that looks quite good. So it's not exactly the same, but overall the curvature distribution does match between what was generated and what was measured on the real CT scan. One thing here, the curvature distribution is not what was directly outputted from FiberGeo, because there's sometimes a bit of an error on that too, but we ran FiberFind again on the generated structure to have the same measurement method and not two different measurement methods to estimate the curvature distribution. And on the right side, we have the thickness estimation from MudDict. That matches okay. It's not perfect because the model at the moment has some constraints for that, but they can easily be changed. It's a bit more homogeneous, less steep entry, but we can already see that the steep entry here is pretty similar to the real one. So like the real one, the upper side is less dense than the lower side. And then we also have the flow simulation. So here the flow fields into two samples and the associated permeabilities. As I mentioned, quite close in permeability, even You can see these high flow velocity regions. There are like 3 here, and we also have kind of 3 over here. So it's a very nice agreement. Yeah. That's it for the results for the nonwoven. Of course, one could do a lot more here. We can look at maybe saturation curves. We can look at pore size distributions. So there's still a lot of room to research how well our results in and compare them with the real thing. And then, as I already talked about earlier, we have one slide about the digital twin for granular media here that is already in Geodict, where we have here a 2D SEM image that is segmented, and we can then generate from this 2D image a 3D digital twin, assuming the direction doesn't play a role. So every direction is the same. Yeah, with that, I come to the discussion slide. As I mentioned, the current version is only one layer with one type of fibers, so a lot of room for improvement. You can go in the code and change it. If you have ideas, let me know. And yeah, thank you for your attention.